Welcome to GDP's Game Engine Frameworks and Patterns 2019. My name is Felipe Bellini, and this is a video demonstration of Project 1, addressing the classes lectured by Michael Finney at Fanshawe College. All the information and source regarding this project can be found at both GitHub and Fanshawe Online. Project 1 features software development patterns, strategies, and best practices. For this proof of concept, we'll be looking at inheritance, factory, builder, mediator, singleton, and pointer to implementation patterns. Now let's take a look at the code. Open Project 1 solution using Visual Studio 2019. If you have already seen the Project 1 of either graphics or physics, know that this project is a continuation of those works. Although we can find usage of patterns in both Bell Engine and OpenGL-Proj, I'll be focusing on OpenGL-Proj, which is the game itself in this scenario. Before continuing with this presentation, I'll run this project once for a little bit of context. The mechanics for this demo is a space battle scene where the player controls a ship that can move using the WASD key or E keys and shooting enemies with the spacebar. Once an enemy dies, it is respawned at a random location just above the terrain. Only one enemy will appear at a time. In addition to that, every 10 seconds a crate of weapons may be spawned on top of the terrain. This will only happen if there is no loot available to the user. If the player collides against the terrain, its position is corrected and the speed is reduced. But if it collides with an enemy UFO, then it's game over. If the player collides with a weapons crate, its active weapon will change randomly between rockets and bombs. Rockets will always be fired from the front of the ship, while bombs will be dropped from below. Let's take a quick peek. The first topic is inheritance. Inheritance is a pattern that enforces objects to derive following down a family tree. Parent objects usually contain properties that are common between all of its children. These can come in shape of base classes, interfaces, and so on. We'll be examining the iWeapon interface. This provides a basic connection to all weapons in the game. As example, we have Weapon Rocket and Weapon Bomb classes. Although they may be different from one another, they will share the same base through the iWeapon interface. As you can see, the Weapon Bomb has an explosion radius, but shares the same ID and name and damage from the Weapon Rocket. These are defined by our interface iWeapon. iWeapon is an implementation called pure virtual and cannot be instantiated by a developer. Developers can only interact with it through its children objects. At this point, we can test the idea of inheritance by creating a new type of weapon, and then start talking about factories. So, in code, I'm going to create a weapon railgun class and see how this impacts the compilation. So we have our weapon railgun implemented here. Let's compile the code and see how it affects the compile. Okay, so the addition of weapon railgun only compiled weapon railgun.cpp. Let's include the weapon railgun in the weapon factory and see how that affects the rest of the code. A factory is a parent that basically isolates the creation of objects. This is particularly useful for encapsulation, avoiding different points of the code where users are calling new at will on any object. We can have a separate factory class or make our objects provide their own factories. In our weapon factory, we will see the getWeapon method. This creates instances of bombs, rockets, and the new railgun that we just created. This is then returned as instances of the parent I weapon. We're going to add our new railgun to our factory. Before doing that, let's go back to our weapon railgun and make the I weapon public. This will give access to the I weapon properties on the factory. Okay, great, now we have it. Let's compile. As expected, only the weapon factory and the weapon railgun were compiled. Notice that the classes that make use of weapon factory do not get compiled. This would be the case for the battlefield Pimple, which has an instance of weapon factory. Let's move on to the builder pattern. The builder pattern is an extension of the idea presented by factory. Builders will combine different objects into another one. These objects may not necessarily be related to one another. The following example will demonstrate the use of a builder to construct a level. Levels are defined by an external XML file that's loaded on the main of the game. Our builder class is here called Level Loader. The level loader will translate the content of the XML into a single level object. Levels can currently contain the camera, game objects, and lights. This one particular method loads game objects. As you can see, it's reading the XML file and bringing the content to the game object. Here it's translating the mesh or the rotation of the game object, its color, and etc. This piece of code will read from the XML and decide, for instance, what's the shape of the rigid body surrounding the game object, building it accordingly. As we can see, it's trying to decide if that's a sphere or that's an ABB or mesh, which will end up creating either a cube or a sphere. This also illustrates the use of builders and factories at the same time. GetBoundingSphere and GetBoundingCube are sphere and cube generators or factories per se. And this builder is upgrading the position of the cube in relation with the position of the game object. Another example of builder can be seen in our battlefield classes. These classes represent our world itself and builds on top of the level and many other objects that are created during runtime. The constructor for our battlefield Pimple will build the world by using the data we acquired from the level. These methods are all builders. SetWorld, for instance, will find out what are the highest points in this terrain we have, and the shape of the terrain, and getting the max and minimum bounds of it. In other methods, such as setFoes, we'll find the player and the UFOs and attribute life values to it, health values to them, for instance. And the set weapons will create weapons according to what weapons are available on the game objects definition. Our next topic is the mediator pattern. As seen in class, the mediator uses messages to communicate changes or cause actions that affect objects that are not necessarily related. Let's take the battlefield object as an example. Our battlefield, which represents our world, makes use of this pattern. It is capable of receiving messages and treating them as it deems fit, so other objects do not need to do any heavy lifting to relate objects together. I have created a message class and interfaces to support this implementation. This can be found inside Bell Engine project. The iMessage listener allows children to listen to messages. Messages can store data in a vector of void pointer parameters and use its header as identification for the classes that are receiving the message. The constructor for message will receive its header and any number of parameters. Now, we're back in our main code to see how the mediator is being used. In our main, we have a collision response method that makes use of it. For instance, if the player collides with the terrain, two messages are sent. One to push the player away from the terrain, the other one to dump its speed. In another example, it shows what happens if the player collides with the foe. Both foes are destroyed, which means the player dies and it's game over. In addition to that, our user control class is also making use of the mediator. Here we have the keyboard callback. We have, for instance, when the user presses the fire or the spacebar, a fire weapon message is fired. Let's see what happens inside Battlefield. The Battlefield has an implementation for receive message. That's in iMessage listener. Here we have messages to cause damage, destroy all objects, update position, damp speed, fire weapon, take weapon, and end the game. If you look into destroy all objects, for instance, it has a protocol. The protocol is receiving the destroy all as the header of the message, then a number of parameters that needs to be larger than 0. All the parameters needs to be the name of the objects. In another example, we have the fire weapon. The fire weapon will simply be received without any parameters. It doesn't care about the number of parameters. It finds the weapon to be fired and do what's asked to be done. Fire the projectile towards whatever is the position of the object. If you're familiar with C#, the mediator is quite common in design patterns such as MVVM. There's a great implementation of that in MVVM Lite. Now to the singleton pattern. This prevents objects from being created more than once by a developer. Singleton objects have their constructor hidden from any outsider. Instead, they'll give a static creating instance method that will initialize a static instance of the object if the object is non-existent. Else, it will always return the static object back to the developer. I have created an interface to define a singleton. That's a singleton in Bell Engine. Here, singletons are required to be able to create an instance of an object and dispose it. There are many examples of singleton in our game. For instance, the camera is a nice singleton. It contains a static pointer to itself, as well as static methods for creating new instances and dispose it. Let's take a look at its implementation. Here's the implementation of camera. Here's the object, static, and here's the created instance. In the case of camera, it will test if the camera static object is initialized. If this object is real, is not null, then it returns the object back to the developer. Otherwise, it will create a new instance of it. This makes sure that only one camera will exist at a time. The dispose function will delete the static camera object. The camera is created in our level loader. Which, by the way, is another singleton. Here we have it. The camera of the level being initialized. Get instance is being called here. Our last pattern is pointer to implementation. Pimple allows code separation, causing objects to become wrappers of their own implementation. Think of this as APIs that will orbit a core object. In our proof of concept, the Pimple implementation is represented by the battlefield objects. The battlefield.h header represents the API. It contains a pointer to its own implementation. This is initialized once its constructor gets loaded. Its implementation is as follows. In another pattern, this will be the private methods and properties of the battlefield class. If we go into the battlefield object, or the API, we can see its pointer to implementation being initialized, and then being used across the battlefield object. Like this, for instance. There's a getLevel function that returns the level that's inside the pointer to implementation. Once the battlefield gets disposed, it will get rid of this object. Like this. Now let's change something inside our implementation object and see how that affects compile time. Ideally, only the battlefield objects should be compiled. Any portion of the code that's making use of the wrapper class should not be compiled. Let's go into the header of our Pimple object and create a new method and maybe a new property. Okay, let's compile. Okay, great. As I was expecting, our console window is telling us that only the battlefield and its implementation are being compiled. That concludes this video demonstration. For more information, contact Felipe Bellini or Michael Finney at Fanshawe College. Thank you.